In the autumn of 1940, a physicist named Edward Bowen carried a metal deed box across the Atlantic. The box was the kind used to store property documents, unremarkable in appearance, small enough to fit on a desk. Inside it was a device that looked like a copper cylinder the size of a man's fist, with a hole bored through the center and 8 smaller cavities machined around the circumference. It weighed less than a pound. It had no moving parts. It had been built in a laboratory at the University of Birmingham by 2 scientists named John Randall and Harry Boot, refined into a sealed production prototype by an engineer named Eric Mega at the General Electric Company's research laboratory in Wembley, and entrusted to Bowen as part of a secret delegation that would change the course of the war. The device was called a cavity magnetron. It generated microwave radio pulses at a wavelength of 10 centimeters with a power output of 10 kilowatts. To understand what that means, understand this. The most powerful microwave transmitter in the United States at the time, a device called a klystron, produced 10 watts, not kilowatts, watts. The British magnetron was 1,000 times more powerful. The Americans had nothing remotely comparable. Nobody did. The cavity magnetron was, in the opinion of the official historian of the Office of Scientific Research and Development, the most valuable cargo ever brought to American shores. More valuable than gold, more valuable than blueprints for the atomic bomb, which were also carried on the same mission, because the magnetron was not a theoretical possibility, it was a working device. It was ready to be manufactured, and it solved a problem that was, in the autumn of 1940, killing Britain. The problem was the U-boat. German submarines were strangling the Atlantic supply lines that kept Britain alive. Every ton of food, every barrel of oil, every crate of ammunition that Britain consumed had to cross 3,000 miles of ocean from North America, through waters patrolled by German submarine wolf packs that were sinking Allied merchant ships faster than they could be built. In the first year of the war, U-boats sank over 1,000 ships. By 1942, the worst year, German submarines destroyed over 6 million tons of Allied shipping, an average of more than 500,000 tons per month. Merchant sailors died by the thousands, their ships torpedoed in the darkness, their lifeboats adrift in freezing water hundreds of miles from land. For every convoy that reached Britain, cargo ships went down in flames, their loads of grain, fuel, and weapons settling to the bottom of the Atlantic.
Churchill would later write that the only thing that truly frightened him during the war was the U-boat peril. Not the Blitz, not the fall of France, not the Japanese advance in the Pacific. The U-boats. Britain was an island that imported half its food and virtually all its oil. If the Atlantic supply lines were severed, the population would starve within months. The war effort would collapse. There would be no buildup of American forces in England, no invasion of occupied Europe, no second front to relieve the pressure on the Soviet Union. The entire Allied strategy depended on the ability to move cargo across 3,000 miles of ocean through water infested with submarines that were becoming more numerous, more lethal, and more skillfully commanded with every passing month. The existing defense against submarines was inadequate for a simple reason: you cannot kill what you cannot find. Escort vessels could detect a submerged U-boat using sonar, the underwater sound-ranging technology developed during the First World War. A sonar operator would send a pulse of sound through the water and listen for the echo bouncing off a submarine's steel hull. The system worked within limits against a submerged target. But U-boats in 1940 and 1941 spent most of their operational time on the surface. They were faster on the surface than submerged. Their diesel engines, which could not operate underwater, charged the batteries that powered the electric motors used for submerged running. And they attacked on the surface at night when they were invisible to escort ships scanning the dark ocean with binoculars and searchlights. A surfaced U-boat was a narrow, low silhouette barely rising above the waves, virtually impossible to see in darkness or bad weather. The existing radar sets, operating at long wavelengths of 1.5 meters, were too crude to detect such a small target. The radar antennas required for those wavelengths were enormous, mast-mounted arrays that could not be fitted to aircraft. And it was aircraft that were needed most desperately. An airplane could cover hundreds of square miles of ocean in an hour, whereas a surface escort was limited to the narrow cone of water around its convoy. An aircraft with effective radar could patrol vast stretches of ocean, find a surfaced submarine, attack it with depth charges, and move on to the next patrol sector. But no aircraft could carry a radar antenna large enough to work at meter wavelengths. The technology gap was killing thousands of sailors and threatening to lose the war. What was needed was a radar that operated at much shorter wavelengths. A 10-centimeter radar could use a small focused antenna that would fit inside an aircraft. It could detect a surfaced submarine at ranges of several miles, even at night, even in fog. It could turn a map-like image of the sea surface, distinguishing a submarine's conning tower from the surrounding waves. It could turn the night, which had been the U-boat's ally, into the U-boat's death trap. But generating powerful microwave pulses at 10 centimeters required a transmitter tube that did not exist until Randall and Boot built one in their Birmingham laboratory on February 21, 1940. The story of the magnetron begins with a question that sounds simple and is not. How do you make electrons oscillate at microwave frequencies? Radio waves are generated by electrons moving back and forth in a conductor, oscillating at the desired frequency. For long-wavelength radio, this is straightforward. The electrons oscillate in an antenna driven by an electronic circuit that controls the frequency. But as the desired wavelength gets shorter and the frequency gets higher, the electrons need to oscillate faster, and conventional vacuum tube circuits cannot keep up. The components become too large relative to the wavelength. The electrons cannot change direction quickly enough. The energy dissipates as heat instead of radiation. By the late 1930s, the practical limit of conventional vacuum tube technology was around 50 centimeters. Getting to 10 centimeters required a fundamentally different approach. Randall and Boot found that approach by thinking about the problem from the opposite direction. Instead of trying to drive electrons at microwave frequencies using external circuits, they created a structure where the electrons would naturally oscillate at the desired frequency because of the physical geometry of the device itself. They machined 8 cylindrical cavities into a solid copper block, arranged in a circle around a central vacuum chamber. A cathode in the center emitted electrons. A powerful magnet forced those electrons into a spiraling orbit around the cathode. As the electrons swept past the openings of the cavities, they induced electromagnetic oscillations at a frequency determined entirely by the physical dimensions of the cavities. The cavities acted as resonators, like the body of a guitar amplifying the vibration of a string. The result was a burst of microwave energy at 10 centimeters at a power level that astonished everyone who measured it. 400 watts on the first test, then rapidly kilowatts. The British government recognized immediately that the magnetron was a war-winning technology, but Britain in 1940 could not exploit it alone. The country was under bombardment. Its factories were producing Spitfires and Hurricanes and tanks and ammunition at maximum capacity. There was no surplus industrial capacity to develop and manufacture a new generation of radar systems based on an untested laboratory device. The magnetron needed to go to America, where the factories were intact, the workforce was enormous, and the industrial capacity was unmatched. Winston Churchill authorized the Tizard mission, a secret scientific delegation led by Sir Henry Tizard, chairman of the Aeronautical Research Committee, to carry Britain's most advanced technical secrets to the United States in exchange for American financial and industrial support. The journey itself was an exercise in wartime absurdity and barely contained disaster. The magnetron and other secrets were gathered in a metal deed box. Bowen was allowed to take magnetron number 12 with him personally. The night before departure, the device sat under Bowen's hotel bed. The next morning, an overeager railway porter at Euston Station snatched the box from Bowen's hands and nearly disappeared with it into the crowd before Bowen wrestled it back. The most valuable piece of military technology in the world was nearly lost to a helpful baggage handler. The delegation crossed the Atlantic aboard the Canadian Pacific liner Duchess of Richmond, arriving in Halifax on September 6, 1940, and proceeding to Washington a few days later. The team assembled on September 12 and began a series of meetings with the American National Defense Research Committee. The initial meetings were cautious. The British were offering everything. The Americans were still deciding what to share in return. Then, Bowen revealed the cavity magnetron. The reaction was electric. The American NDRC Microwave Committee was stunned at the power level. Bell Telephone Laboratories X-rayed the device and discovered it had 8 cavities instead of the 6 shown on the British drawings, a discrepancy that was eventually traced to a production decision by Mega to make one prototype with 7 cavities and one with 8, just to see what happened. Number 12, the 8-cavity version, happened to be the one chosen for the mission. Bell Labs built copies. Within weeks, the foundation was laid for a radar development program that would dwarf anything either country had attempted before. The Massachusetts Institute of Technology established the Radiation Laboratory, known as the Rad Lab, on October 11, 1940, dedicated to developing microwave radar systems based on the cavity magnetron. The Rad Lab would eventually employ nearly 4,000 people and become the second largest wartime research project in the United States, behind only the Manhattan Project. Its researchers included future Nobel laureates and some of the most brilliant physicists and engineers in the Western world. But the Rad Lab designed radar systems. Somebody had to build the magnetrons themselves. Somebody had to figure out how to manufacture a complex, precision vacuum tube device, not in dozens or hundreds, but in tens of thousands, month after month, with consistent quality and reliable performance. That somebody was Raytheon. The Raytheon Manufacturing Company was based in Cambridge, Massachusetts. It had been founded in 1922 as the American Appliance Company by physicist Charles Smith and engineers Lawrence Marshall and Vannevar Bush, the same Vannevar Bush who would later direct the entire American wartime research establishment as chairman of the Office of Scientific Research and Development. The company had built its early reputation on vacuum tubes for radios and had grown into a mid-sized electronics manufacturer. But it was not a giant. It was not General Electric or Westinghouse or RCA. It was a capable, scrappy company with good engineers and a particular expertise in the design and manufacture of vacuum tubes. The man who would make the magnetron a mass-produced weapon was Percy Spencer, and his biography reads like an American myth so improbable that if you put it in a novel, the editor would cut it for being unrealistic. Spencer was born on July 19, 1894, in Howland, Maine, a tiny town in the central part of the state. His father died when he was 18 months old. His mother, unable to cope, left him with his aunt and uncle. His uncle died when Spencer was 7. He and his aunt traveled around New England, she working as an itinerant weaver, the boy taking whatever jobs he could find. He left grammar school permanently to work, entering a spool mill at age 12, laboring from sunrise to sunset, 6 days a week. He would never finish grade school, he would never attend high school, he would never enroll in a college or a university or a technical institute of any kind. At 16, he heard that a nearby paper mill was installing electricity, a technology he had never encountered, and he talked his way into a job on the installation crew despite having no training or experience whatsoever. He taught himself electrical theory by reading textbooks at night. When the Titanic sank in 1912 and the newspapers published stories about the heroism of the ship's wireless radio operators, the 18-year-old Spencer became fascinated by radio technology. He joined the Navy to become a radio operator and spent his watch hours studying trigonometry, calculus, chemistry, physics, and metallurgy from borrowed textbooks. He taught himself standing watch at night, as he later recalled, absorbing entire fields of knowledge through sheer force of will. After the First World War, Spencer joined the tiny American Appliance Company in Cambridge, Massachusetts, which would later be renamed Raytheon. The company had been co-founded by Vannevar Bush, the same Vannevar Bush who would later direct America's entire wartime scientific enterprise. Spencer rose rapidly through the ranks on the strength of his extraordinary intuitive understanding of how electronic devices worked. He could look at a vacuum tube and understand its behavior in a way that formally trained engineers could not match. He noticed things other people overlooked. Early in his career, he discovered that a small leak in a photoelectric tube actually increased its efficiency, a finding that had implications for television camera development. By 1939, he was one of the world's leading experts in radar tube design and had been appointed chief of Raytheon's power tube division. Vannevar Bush said that Spencer had earned the respect of every physicist in the country, not only for his ingenuity, but for what he has learned about physics by absorbing it through his skin. A colleague offered a more practical assessment. The educated scientist knows many things that will not work. Percy does not know what cannot be done. When the contract to mass-produce magnetrons arrived at Raytheon, the company faced a manufacturing challenge that seemed insurmountable. They were producing 17 magnetrons per week. 17! Each one was essentially hand-built, a precision assembly of copper cavities, ceramic insulators, metal cathodes, glass-to-metal vacuum seals, and permanent magnets, requiring skilled technicians who understood vacuum physics, metallurgy, and precision machining. Each unit had to maintain a vacuum seal that would not leak under thermal cycling and mechanical vibration. Each cavity had to be machined to tolerances that determined the operating frequency of the device. A magnetron that oscillated at the wrong frequency was useless. A magnetron with a vacuum leak was useless. The reject rate was high, and the learning curve was steep. The military needed thousands per month, and eventually tens of thousands. The gap between what Raytheon could produce and what the war demanded was absurd.
Spencer stared at the problem with the intensity of a man who had taught himself calculus by reading textbooks on the night watch. The story, told and retold within Raytheon until it became corporate legend, is that he was sitting at his desk one day, deep in thought, fidgeting with a handful of coins, stacking them and restacking them on the desktop, when the solution crystallized. The magnetron's internal structure, the ring of cavities machined into the copper anode block, could be manufactured using a stamping and laminating process conceptually similar to the way coins are struck from metal blanks. Instead of machining each cavity individually on a lathe, a slow and skill-intensive process, the cavities could be punched out of copper sheet and the components stacked and soldered together in a sequence that was fast, repeatable, and amenable to mass production. Spencer designed a system that worked like a cookie cutter for magnetron components. He redesigned the manufacturing process from the ground up. He created jigs, fixtures, soldering techniques, and assembly sequences that broke the construction of a magnetron into discrete steps that could be performed by workers without years of vacuum tube experience. Many of the workers who staffed the expanded production lines were women entering the industrial workforce for the first time, learning to assemble precision electronic devices under Spencer's training programs. The process was not a dumbing down of the technology. It was a translation of craft knowledge into industrial procedure. Every step was documented, every tolerance was specified, every solder joint was inspected. The result was a magnetron that was as good as the hand-built originals but could be produced in a fraction of the time. The results were staggering. Production went from 17 magnetrons per week to 100 per day. Then it climbed further. Eventually, Raytheon was producing 2,600 magnetrons per day. The power tube division that Spencer led grew from 15 employees to over 5,000. Raytheon, which before the war had been a mid-sized electronics manufacturer in Cambridge, Massachusetts, was transformed by the magnetron contract into one of the most important defense contractors in the United States, a position it has held through 8 decades, multiple wars, and the entire arc of the Cold War and beyond.
The company that started by making radio tubes became the company that made Patriot missiles, a trajectory that began with Percy Spencer's insight about stacking copper like coins. The magnetrons flowed from the Raytheon factory in Waltham, Massachusetts, into radar sets that were installed in escort aircraft, in patrol bombers, in warships, and in shore-based stations. The radar systems built around the cavity magnetron transformed the Battle of the Atlantic. Aircraft equipped with 10-centimeter airborne radar could detect a surfaced U-boat at ranges that made escape nearly impossible. The Mark 24 ASV air-to-surface vessel radar, operating at the microwave frequencies enabled by the magnetron, could spot the tiny target of a submarine's conning tower protruding from the ocean at night or in fog. Coastal Command aircraft patrolling the Bay of Biscay, the transit route that every U-boat based on the French coast had to cross, submarines that had previously crossed the bay on the surface with impunity were now being detected and attacked, day and night, in all weather conditions. The closing of the mid-Atlantic air gap, the stretch of ocean beyond the range of land-based patrol aircraft where U-boats had operated with virtual immunity, was achieved in part by equipping very long-range B-24 Liberators with microwave radar. The submarines began dying in numbers that the German Navy could not sustain. In May 1943, a month the Germans remembered as Black May, 41 U-boats were destroyed. The loss rate was 1 submarine for every merchant ship sunk. That ratio was unsustainable. Admiral Karl Donitz, commander of the German submarine force, temporarily withdrew his boats from the North Atlantic. It was an admission of defeat, though the submarine campaign would continue in reduced form for the rest of the war. The tonnage of Allied shipping lost to submarines dropped from over 500,000 tons per month in early 1943 to a fraction of that by mid-year. The supply lines to Britain, which had been hemorrhaging ships and cargo, stabilized and then strengthened. The buildup of American forces in England for the invasion of France could proceed without the constant fear that the transports and cargo ships would be torpedoed en route. The Germans knew something had changed, but for months they did not know what. Their radar warning receivers, tuned to detect the older long-wavelength radar transmissions, were silent when the new centimetric sets were in use. The U-boats surfaced at night expecting the safety of darkness, and instead found aircraft diving out of the black sky with searchlights blazing and depth charges dropping with lethal accuracy. German submariners called the new technology an invisible eye. They could not detect it. They could not jam it. They could not explain to their commanders how the British were finding them with such unerring precision in conditions that should have made detection impossible. German scientists eventually identified the shorter wavelength and began working on countermeasures, but the development cycle took time they did not have. By the time effective countermeasures were deployed, the Battle of the Atlantic had been decided. The cavity magnetron's impact extended far beyond the ocean, reaching into every theater and every dimension of the war. Microwave radar sets based on the magnetron were installed in bomber aircraft, giving them the ability to navigate and identify targets through solid cloud cover that had previously made precision bombing impossible. The H-2S radar system, developed in Britain using the magnetron and first deployed by RAF Bomber Command in January 1943, projected a map-like image of the ground below the aircraft onto a cathode ray tube in the navigator's station. Rivers appeared as dark ribbons. Cities appeared as bright clusters. Coastlines were clearly delineated. For the first time, bomber crews could identify targets on the darkest, most overcast nights when the ground below was invisible through 10,000 feet of solid cloud. The system was not perfect. Urban areas sometimes blurred together. Isolated targets in open countryside were difficult to distinguish. But compared to the blind navigation that had preceded it, H-2S was a revolution.
The American equivalent, designated H-2X and operating at the shorter X-band wavelength of 3 centimeters, was used by the 8th Air Force for bombing through the perpetually overcast skies of northern Europe. In the autumn and winter months, when solid cloud cover over Germany could persist for weeks at a time, H-2X allowed the strategic bombing campaign to continue on days when visual bombing was impossible. Without it, the bomber offensive would have been limited to the handful of clear days that occurred in a typical European winter, a restriction that would have dramatically reduced the pressure on German industry. Microwave radar was installed in night fighters on both sides of the English Channel, giving interceptor pilots the ability to find and track enemy aircraft in total darkness. The AI Mark 8 radar, a centimetric set based on the magnetron, allowed RAF night fighters to close on German bombers that had previously been invisible in the night sky. The technology transformed the defensive night air war over Britain and, later, the offensive night fighter campaign over occupied Europe. Ground-based microwave radar was used for precise tracking of aircraft, for anti-aircraft gun laying, for ground-controlled interception of enemy formations, and for directing the complex air traffic of large-scale bombing operations. The cavity magnetron, designed to find submarines, had become the enabling technology for an entire ecosystem of radar applications that touched every aspect of modern warfare. The Rad Lab at MIT, which had been established in haste to develop radar based on the magnetron, grew into one of the greatest concentrated efforts of scientific and engineering talent in human history. At its peak, it employed 3,500 people, including physicists who would go on to win Nobel Prizes, engineers who had found the great post-war electronics companies, and technicians whose skills would seed the American high-technology industry for decades to come. The lab occupied 15 acres of floor space in buildings that had been hastily constructed or requisitioned on and around the MIT campus. It consumed more electricity than a small city. It operated around the clock with the intensity of men and women who understood that the devices they were building were deciding the outcome of battles being fought that same day on oceans and in skies thousands of miles away. When the war ended, the Rad Lab published a 28-volume technical series that became the foundational reference for radar and microwave engineering. The series was so comprehensive and so well written that engineers were still consulting it decades later. The Rad Lab's alumni went on to staff the electronics laboratories of the Cold War, to build the early computer industry, and to create the technological infrastructure of the modern world. Commodore Jennings Dow, head of electronics at the U.S. Navy's Bureau of Ships, summarized the contribution succinctly. Raytheon radar had a marked effect on every major sea engagement of the war.
And then there was the accident. One day in 1945, Percy Spencer was standing near an active magnetron in the Raytheon laboratory when he noticed that a candy bar in his pocket had melted. The observation would have been meaningless to most people. Spencer was not most people. He was the man who did not know what could not be done. He sent for popcorn. He held the kernels near the magnetron. They popped. He brought in an egg the next morning. He directed the microwave beam at it. The egg exploded, splattering the face of a colleague who was peering at it too closely. Spencer understood immediately what was happening. The microwaves emitted by the magnetron were causing water molecules in the food to vibrate, generating heat through friction. He built a metal box to contain and concentrate the microwave energy, placed food inside, and watched it cook. On October 8, 1945, Raytheon filed a patent for a microwave cooking process. The first commercial microwave oven, the Radarange, went on sale in 1947. It was 6 feet tall, weighed 750 pounds, and cost $3,000. It took 20 years for the technology to shrink to countertop size and drop to a price that ordinary consumers could afford. By 1975, microwave oven sales in America exceeded gas range sales. Today, over 90% of American households have one. Every single one contains a cavity magnetron, the direct descendant of the device that Randall and Boot built in Birmingham in 1940.
The arc of this story stretches from a university laboratory in England to a submarine in the North Atlantic to a kitchen in suburban America. A device invented to win a war became a device that reheated leftovers. The magnetron that found U-boats in the darkness of the ocean now thaws frozen dinners in the light of a kitchen. The transformation is so complete, so mundane, that nobody thinks about it. Nobody standing in front of a microwave at midnight, warming up a cup of coffee, pauses to consider that the humming device in front of them is a direct descendant of a weapon that changed the outcome of the greatest naval battle in history. Percy Spencer died on September 8, 1970, in Newton, Massachusetts. He held over 300 patents. He had never finished grammar school. He received the Distinguished Public Service Award from the United States Navy for his wartime contributions and an honorary doctorate from the University of Massachusetts, an institution he had never attended as a student. Raytheon named a building after him at their Woburn facility. He retired as a senior vice president of the company, a man who had entered the workforce at 12 years old in a spool mill and left it as an executive of one of the largest defense corporations in the world.
But his real monument is not a building or a plaque or a patent filing. His real monument is everywhere. It is in every kitchen where a microwave oven hums to life. It is in every air traffic control tower where a radar screen paints the positions of aircraft across 100 miles of sky. It is in every weather radar station and every police speed gun and every satellite communication system and every cell phone tower. The cavity magnetron, mass-produced by a self-taught orphan from Maine who figured out how to stamp them like coins, is one of the foundational technologies of the modern world. And it began with a copper cylinder the size of a fist, carried across the Atlantic in a metal deed box that nearly fell off a taxi at Euston Station during the darkest year of the war by men who understood that the future of civilization depended on the ability to see in the dark. They could not see the future. They could not know that the device in their box would find submarines and save convoys and turn the tide of the Atlantic, and then, in a final act of transformation so unlikely it borders on comedy, melt a candy bar in an engineer's pocket and give the world a way to reheat last night's dinner in 90 seconds. That is how history works. Not in straight lines, in ricochets.